Yes, sir.
What's the program?
Sir, nothing much, sir.
Okay, what is that little?
Sir, nothing, sir. Just studies. That's it.
I'm coming to meet you tomorrow, possibly in the evening.
Okay, sir.
Hmm.
Please come, sir.
Yes, yes. What's going to be the treat for me?
Sir, as you wish, sir.
Okay.
Sir, you can start, sir.
Yes, ma'am. Yes, ma'am. Only Ajay is there. Nobody else is joining today, ma'am.
No, sir, they will join, sir.
So shall I start now or wait for 2-3 minutes?
No, sir, you can start.
Start. Okay. Yesterday we were learning, Ajay, we were learning about the molecularity and order. We'll continue.
Yes,
Today few derivations we have to do, and based on those derivations, problems we'll have to solve. This class will be most important in this chapter, kinetics. So just to have the continuity, we will learn what we did yesterday. We learned two definitions. One is molecularity, the other one is order. Now, we know the definition. Molecularity is minimum number of reacting molecules taking part in the slow step of the reaction or elementary reaction. Depending on the number of molecules taking part, we have different types of molecularity: unimolecular, bimolecular, and termomolecular reaction. And we learned that molecularity is determined theoretically by a completely balanced equation. Completely balanced equation. And order is defined as sum of the powers of the concentration terms. If I write the rate equation and we write it as A and B are the reactants and the X and Y. So the order of the reaction is sum of X and Y. What is order? Order is defined as sum of the powers of concentration terms in experimentally determined rate equation. Experimentally determined rate equation. So this rate equation, what I've written, it's not based on the law of mass action. This is the rate equation which we are determining experimentally. Now for a reaction, A plus B giving you the product. A and B are the reactants. See, the coefficients of A and B are 1 here, but we have written the coefficients as what? X and Y. Some of the powers of the concentration terms in an experimentally determined rate equation is called as order of a reaction. We learned the methods of determining the order. Now, 4 methods. You have to remember the methods, not in detail, that explanation part. It's there in the class material in the video. If you want, you can just go through, but it's not necessary. The first one is integrated method. Integration method. Integration is a mathematical concept. Integration method, the first method of determining the order. Second is half-life period. This half-life period method, this we are going to learn. What is half-life period? We are going to learn. Third, what we have is graphical method. Graphical method. And the fourth, what we have is called as Oswald's isolation method. This is the fourth method. So 4 methods we can determine the order of the reaction. One is by integration method. The other one is by the half-life method. Third is graphical method. The fourth is Oswald's isolation method. Now you can see graphical method. So many graphs are represented. These concepts, we'll understand later. It's not there in the syllabus, but I want you to remember the methods in which we can determine the order of the reaction. One is integration method. This is also called as what? Heat and trial method. The second one is half-life method. Third is graphical method. And the fourth is by Oswald's isolation method. This is what we learned yesterday. Now we're going to continue with the topic. All right. Now, order can be zero. Difference between molecularity and order also we have learned in detail. Now, just observe this equation. In this equation, this is a rate equation. This is a rate equation. I'm asking you a question. Now, there are three, A, B, and C, three reactants, A, B, and C. Now, what is the order with respect to A? What is the order with respect to A? The order with
It's a two,
respect to
sir.
A is 2. Yes. The order with respect to B is what? 1.
One, sir.
And order with respect to C is 0.
So
We learned different ordered reaction also yesterday. First order, second order, fractional order, zero order reaction, as well as I taught you pseudo false order reaction also. Pseudo unimolecular reaction also I taught you last class. Pseudo unimolecular reaction, false unimolecular reaction. Now, example I gave you was ester, methyl acetate. When we hydrolyze this in the presence of an acid, what happens is H gets bonded here and OH gets bonded here. The cleavage I'm showing. So you get CH3COOH and CH3OH. This is acetic acid and this is ethanol. Now, as per the law of mass action, if we write rate is directly proportional to concentration of methyl acetate and concentration of water. Now, concentration of methyl acetate, with respect to methyl acetate, the order is 1. With respect to the order with water is 0. Why? Because this water is taken in large excess. When we take concentration of water or any other reactant in large excess, the concentration remains almost constant. When the concentration remains almost constant, the order with respect to that particular reactant is considered to be 0. Now here in a reaction ABC, concentration with the order with respect to C is considered to be 0. It means the concentration of C would be in large excess. Now for this particular reaction, the molecularity is 2, but the order is 1. Why the order is 1? Because the concentration of water is what? 0, or maybe we can say the order with respect to water is 0. So the order depends only on the concentration of methyl acetate. Therefore, order is 1. So pseudo unimolecular reaction was in which the molecularity is 2 or more, but the order is 1 is called a pseudo unimolecular reaction. This is what a pseudo unimolecular reaction. One of the example. One more example they give, that is hydrolysis of cane sugar. What is the formula of cane sugar? Sugar, C12H22O11. Sugar, what is there in the kitchen, what we eat is called as cane sugar because we get it from sugar cane. Now this, when we hydrolyze in the presence of water, this is otherwise, this is in the presence of acid, sorry. This cane sugar is otherwise chemically called as sucrose. When we hydrolyze, this sucrose will decompose or break down to give C6H12O6 plus we will get C6H12O6. We'll get glucose and you will get a unit of fructose. See, for glucose and fructose, the molecular formula is same. The molecular formula is same. Now here also, if you write the rate equation, rate will be directly proportional to concentration of sucrose into concentration of water. But the order with respect to sucrose is 1, the order with respect to water is 0, because whenever we take a dilute acid, the concentration of water is taken in large excess. When the concentration of water is taken in large excess, the order with respect to water is 0. So molecularity for this reaction is 2 and order of the reaction is 1. So this is also called as hydrolysis of cane sugar. Hydrolysis of cane sugar is also an example for a pseudo unimolecular reaction. Now, I told you a few derivations we have to learn. It is very simple to understand this derivation. Before we understand the derivation, how do we define the rate of a reaction? How do we define rate of a reaction? What is the definition for rate of a reaction? It is defined as the ratio of change in concentration with respect to time. This is the definition for the rate of a reaction. Rate of a reaction is defined as the ratio of change in concentration with respect to time. Now, how do you define rate of a reaction with respect to reactant? Now, what should happen? The concentration of reactant has to decrease. Decrease in concentration of the reactant with respect to time. This is the definition for rate of a reaction. with respect to reactant. What will be the rate of a reaction with respect to product? What should happen when a reaction is taking place? The concentration of the product has to increase. Increase in concentration of the product with respect to time. This will be the definition for rate of a reaction. Yes or no? We define or we represent a rate of a reaction as plus or minus dx by dt, or we also represent it as plus or minus dc by dt. I taught you all this in the previous classes. Now, what does this plus indicates? Plus indicates increase in concentration of the product with respect to time, and minus indicates decrease in concentration of the reactant with respect to time. So this is the definition for the rate of a reaction. Rate of a reaction is defined as change in concentration of the reactant with respect to time. All right. Ajay, are you there? Are you following?
Yes, sir.
Jaswant, are you following?
Yes, sir.
Yeah. Okay. I don't know. What's your name?
Jaswant, sir.
Jaswant. Okay. All right. Now, anyways, now we have to derive three relations. We will derive three relations. The first one is derive to calculate the rate constant or velocity constant. It is also called as rate constant. Rate is also called as velocity. So rate constant or what? Velocity constant for a zero order reaction. Or they can ask you derive integrated rate equation. Integrated rate equation for zero order reaction. For zero order reaction, they can ask you derive velocity constant or rate constant for a zero order reaction, or they also can ask you derive integrated rate equation for a zero order reaction, or else we can work problems based on this. Many types of problems are asked based on this, but anyway, this is a 12th standard question. They can ask you for derivation. Now we will derive this what's that rate equation. Possibly here we will derive. It's there printed, but anyways we will do it again. So I will erase this question. So I need space. Right, I need space. So we'll erase this. Now we will consider a reaction. What is the reaction we are considering? R giving you P. Now, what is this R called as? This R will be called as reactant and P will be called as product. Now, can you define, any one of you can define what is law of mass action quickly? Can anyone think of from your memory and tell me what is law of mass action? Hello? If you know, you tell me, otherwise I will repeat it. No problem. Don't keep quiet. So we are wasting time. That's it. Tell me if you can remember, or else I'll tell you.
Exact definition, no, sir.
You don't know the exact definition, okay? But I was teaching you here, rate is directly proportional to product of concentrations of the reactants whose coefficients are raised to their power. So for an example, if I take a reaction A plus B giving you product, the rate of a reaction at constant temperature. The definition is what? At constant, the condition is what? Temperature to be constant. At constant temperature, rate is directly proportional to concentration of the reactants, product of the concentration of the reactants, whose coefficients are raised to their power. Since the coefficients are 1, we have written it as 1, or we don't write it also, it doesn't matter. Now from this, what we understand is the speed of the reaction or the rate of a reaction depends on the concentration of the reactants. It does not depend on the concentration of the product. The speed of the reaction depends on what? Concentration of the reactants. That is what I want you to understand. Now, we are considering a reaction R giving you product. Now, when we have considered a reaction R giving you product, now the rate of a reaction is directly proportional to concentration of what? The reactant. What is the reactant here? R. Can we write it like this? Reactant is R. Therefore, we write it as what? Rate is directly proportional to concentration of R. Is it acceptable? Yes or no?
Sir. Yes, sir.
Now, can I write rate as dr by dt. What is this dr by dt? Change in concentration of the reactant with respect to time. I write it as what? dr by dt. That is what rate is. Rate is defined as what? Change in concentration with respect to time. With respect to reactant, what we write? Decrease in concentration of the reactant with respect to time. So the decrease in concentration we represented by what sign? Minus sign. Can I write it as minus dr by dt? Can I write? This is nothing but what? R. Did you follow what I've written?
Yes, sir.
Now, if I remove the proportionality sign, what we have to give? We have to give a proportionality constant. That's called as what? A rate constant. We represent rate constant to be what? K. And what we have R. And what order we are talking about? What order we are talking about? What order we are talking about? We're talking about?
So 0 or
So what should I write? The power should be what here? 0. The
0.
power here should be 0. Anything to the power 0 is what?
1, sir.
1.
So 1,
So
sir.
1. So what will we write? Minus change in concentration of the reactant with respect to time will be equal to K. Yes or no? Because anything to the power 0 is what? 1. 1 into K is K. Now we will rearrange the terms. When I say we will rearrange the terms, we will write minus change in concentration of the reactant will be equal to K into dt. We'll cross multiply this K into dt. Now we can take the minus sign towards the right. When we take minus sign towards the right, what happens? Change in concentration of the reactant will be equal to minus K into dt. Now integrating both the sides. Integrating both the sides. I don't know in the mathematics whether you have learned integration. Calculation, what is calculus? Differentiation you would have learned. Differentiation and integration is a part of the topic called as calculus. Very good topic. All right. Now integration we represented by the symbol like this. Integration is the reverse of differentiation. Integral of change in concentration of the reactant will be equal to integral of minus K into dt. Minus K into dt. Now, I will erase this side. I'll erase this side. In order to understand the explanation, I'll erase this side. Now, you should remember integral of dx is x. That means when you integrate dx, the answer what you will get is x. When you integrate dt, the answer is t. When you integrate dr, the answer should be what? R. So here the integral of dr is what now? R. Concentration of R. R will be equal to, now you can see here on the right hand side, you have K and you have dt. You have two terms. When you have two terms, there is a rule, UV rule, which will follow. What is that UV rule? Okay. One is integral of K minus K. Wait. This is integral of minus K into dt. So what we do is we keep minus K constant and integrate dt. Plus, now you keep dt constant and integrate K or minus K, whatever it is. Now this is called as UV rule. This is called as UV rule. Did you follow this?
Yes,
Did you
sir.
follow this minus K into dt, how I've integrated? Now
Yes,
this will be equal to what now? Minus K into integral of dt is what? T plus dt into integral of any constant is 0. Integral of any constant is what? 0. So what will be the answer you will get? You will get minus kt. So integral of minus k into dt is what? Minus kt. Now whenever we integrate, we should give an integration constant. We will give that integration constant to be what? I. We will give integration constant to be I. We will mark this as equation number 1. For our understanding, we'll mark this as equation number 1. Now, the next part of the topic is to find the value of I. Find the value of I. What is this I? This I is called as integration constant. Whenever we integrate, we have to give a constant I. In the previous boards, we used to give integration constant to be C. In the NCERT, they have mentioned it to be I. We will use it as I itself. Now, to find the value of I, when I said to find the value of I write at time t is equal to 0. At time t is equal to 0. Do you think any reaction would have taken place? Do you think any reaction would have taken place? When time t is 0, do you think?
sir.
No. When time t is equal to 0, the concentration of the reactant remains as what? The initial concentration. So this R value, the concentration of the reactant becomes what? Initial concentration. So initial concentration, we represent it as what? R naught. Now substitute in equation 1. When you substitute in equation 1, what do we get? When you substitute in equation 1, what do we get? What do we get? We will get R becomes what now? R naught. That will be equal to minus K into time is what? 0 plus I. So what happens? I becomes equal to what? R naught. Did you understand? I becomes equal to what? R naught. Substitute in equation 1. Substitute this value in equation 1. When you substitute in equation 1, what do we get? R
So
is
R is equal to minus KT
minus KT
plus
plus
R
what?
R naught.
R naught. Now rearranging the terms, what we can do? We can take KT to the left-hand side. When you take K to the left-hand side, what happens? The sign becomes positive. And this R you can take to the right side. What happens? What happens if you take this R to the right side? You'll get what sign? Here it's a positive value. If it goes to the right side, what happens? It becomes minus. Yes or no?
Yes, sir.
So what will be this K? K will be equal to concentration of R naught minus R divided by T. This is the rate constant for what order reaction? Zero order reaction. What is R naught? R naught is the initial concentration. Initial concentration. And what is R? It is concentration after time T. Concentration after time T. What do you mean by concentration after time T? After some amount of time, how much of reactant is left out, that is represented by the letter R. So R naught stands for initial concentration and R stands for concentration of the reactant after a certain amount of time T. Did you understand this derivation, students? It's lengthy, but you followed?
Yes, sir.
Yes, sir.
Yes. Yeah. Now we'll have to do one more derivation, or two more derivations today. We will do two more derivations in few minutes time. Before that two derivation, I want you to understand the definition. Now, what's that definition you need to understand? Now, I will write and ask you. Wait. All right. Now, the definition, what we have to learn is called as half-life period. Half-life period. This half-life period is represented as T half, it is represented as T 50%, or it is also represented as T 0.5. Now, what is this half-life period? Now, for an example, what are these? Carbon 12, carbon 13, carbon 14. What are these called as? What are these called as? What are these called as?
Isomers.
Iso?
Isomers.
Iso?
So isotopes, sorry.
Isotopes. They're called as what? Isotopes. MER, isomer, stands for molecules. All right, this is an atom, this is an element. So elements having same atomic number but different atomic mass, they are called as isotopes. Now, amongst these three isotopes, which one of the isotope is radioactive? Which one of the isotope is radioactive?
So 14C, sir.
Very good. Carbon 14 is what? Radioactive. You know the concept of radioactivity. I'm not explaining radioactivity here because radioactivity concept is not learned in chemistry. It's been learned in physics now. All right. Now, carbon 14 is radioactive. Now, I'll take carbon 14 and we will take 5 grams of carbon 14. Now, after 5,600 years, years, if you measure the amount of carbon 14 present, the amount of carbon 14 present is 2.5 grams. 2.5 grams. Initially, carbon 14 is taken how many grams? 5 grams. So after 5,600 years, the estimated amount of carbon 14 is around 2.5 grams. Now tell me, is the amount reduced to exactly 50%? Is the amount of carbon 14 reduced to 50% exactly? Yes or no? Is the amount of carbon 14 reduced to 50%? Yes or no? Here it is 5 grams. Here it is how many grams?
Yes, sir.
2.5 grams. Now, can I put it in other words? In 5,600 years, the amount of carbon 14 reacted is 50%, can I say?
Yes, sir.
Yeah. What does it mean? The time required for 50% of carbon 14 to react is 5,600 years. So that is the definition of half-life period. This is an illustration what I gave you. What is this half-life period? Time taken for 50% of the reaction to complete is called as half-life period. Is called as what? Half-life period. What is half-life period? Time required for 50% completion of the reaction. Maybe we can write time taken for 50% of the reactant concentration to decrease. It's all the same. So in simple words, we can write time taken for 50% of the reaction to complete is called as what? Half-life period. All right. What is half-life period? The time required for 50% completion.
So 50% of the
It is
reaction
very
to be
simple. Do you
completed.
understand this? Time required for 50%
Yes, sir.
completion of the reaction is called as half-life period. If that is the case, the next derivation we will go. The next derivation is here. Now, the relation between a half-life period and zero-order reaction. Calculate the relation between half-life period and the zero-order reaction, or derive to calculate the relation between half-life period and zero-order reaction. Anyways, now we will consider a reaction here. I'm writing it in another color. Consider a reaction, R giving you P. What is this R? R is called as reactant and P is called as product. Now we know that for a zero-order reaction, how is rate constant related? K is equal to concentration of reactant initial concentration minus concentration after a certain amount of time t divided by what? T. We have derived it here. Can you see this? K is equal to R naught minus R divided by T. That is the rate constant of what order reaction? A zero-order reaction. Followed by this, we have considered a reaction, R giving you product, and we know that velocity constant or rate constant of a zero-order reaction is equal to initial concentration minus concentration after a certain amount of time and divided by time, change in time. That's called as rate constant. Yes or no?
Yes, sir.
Yeah. Now I'm asking you a question. When T is equal to T half, what do you mean by T is equal to T half? When time is what? Half-life period, T half. What will be the initial concentration? What will be the concentration R here? What will be concentration R? What will be R? After half-life period, how much of reactant would have reacted? How much of a reactant would have reacted?
So half, sir.
Half. Now, what is the initial concentration here?
So R not.
So what will be half of it? R not by?
By 2.
Okay.
Divided
Now
by
you have
2.
understood this. So what will be K now? K will be substitute. This will mark it as equation number 1. Substitute in equation 1. When you substitute in equation 1, what do we get? We get K is equal to R
So
naught
R
minus
R
R
not
naught
by
by
2, sir.
2 divided by
Divided
what?
by 2, sir. Divided by 2.
So how do I simplify now? How do I simplify this? Can I take LCM? So I can write it as what? 2R naught minus what? R naught divided by 2 divided by what? T. Yes or no? This will take it as what? 1. So what's that? LCM is what? LCM is called as what? Least common factor, whatever it is. No? So 2 into 1 is what? 2 into what? R naught. You get 2R naught. Yes or no? Mathematics, you know. Yes.
Yes, sir.
So what is this on simplification? What is this on simplification? K is equal to 2R naught minus R naught is what? R naught divided by 2 divided by T half, I should write. T half, because T is what? T half here. So here also it is T half. Here also I should write it as T half. So what I can write now? What will be K? K will be equal to R naught divided by 2T half. Yes or no? Understood or not?
Yes, sir.
So I can take T half to the left, K to the right side. So what happens? We can write it as T half is equal to R naught by 2K. We can write. Otherwise, you can write. See here, the representation is here. Anyways, you can represent. This is the relation between half-life period and rate constant of what order reaction? Zero order reaction. You should know these derivations. You should know these formulas to work out the problems. So what is the first formula you are supposed to remember? The first formula you have to remember and derivation you have to remember is what? K is equal to R naught minus R divided by T. Initial concentration minus concentration after some time versus T divided by T. Relation between half-life and rate constant of the zero order reaction, T half is equal to R naught by 2K. We have derived it. Students, are you following? Students, are you following?
Yes, sir.
Yes, sir.
Understood, yes. Now, this is a lengthier reaction. It looks very simple here. It's a lengthier reaction, derivation. I don't know where I can do it. But anyways, now the question is, derive to calculate the velocity constant or rate constant of a first order reaction. Or they can ask you, derive integrated rate equation for a first order reaction. They can ask you, derive an integrated rate equation for a first order reaction. All right. So derive to calculate the velocity constant or rate constant of a first order reaction, or they can ask you derive the integrated rate constant for the first order reaction. Now we will derive this. In order to derive this, I need some space, so we will take this page. You know the definition for half-life, all that. All right, so we'll continue with it now. We are trying to derive the rate constant for what? First order reaction. Rate constant for first order reaction. We are deriving the rate constant for what order reaction? The first order reaction. Right. Students, are you following?
Yes, sir.
Yeah. Now we will derive the rate constant for a first order reaction. Before we derive, we will make some space and try to write neatly all that possible. Now, we have to consider a reaction. Reaction, what we consider will be again same as we considered for a zero. Considering for a zero order reaction. Now, we will write consider. I'll make another table. I'll divide it. Consider a reaction. What is this R called as? R is called as reactants and P is called as product. Now, according to law of mass action, we can write rate of a reaction is directly proportional to concentration of the reactant. What's the reactant here? R. So R is directly proportional to concentration of the reactant. We can write yes or no? Because rate of a reaction depends only on the concentration of the reactant. It does not depend on the concentration of the product. So only one reactant we have, that is marked as R. So rate is directly proportional to concentration of the reactant. Yes or no?
Yes, sir.
You tell me, how do I represent the rate? Can I write it as minus change in concentration or decrease in concentration of the reactant? Sorry, I will write a little larger, this R. Change in minus is indicating the concentration of the reactant is decreasing. Change in concentration of the reactant with respect to time. So if you remove the proportionality sign, what we give? What we give? If you remove the proportionality sign, what we give? A proportionality constant. It's called as what constant? Hello?
Sir,
What is this K called as?
sir, rate constant.
Okay. Now tell me, rate constant K into R, what order we are talking about? First order. Therefore, the power should be written as what? 1. In zero order reaction, do you remember that we have written R to the power 0 because it was a zero order reaction. Now we will rearrange the terms. When I say rearrange the terms, we will write minus change in concentration of the reactant, and I'll bring this R to the denominator by R. That will be equal to, we'll take this minus sign. Okay, we'll write it as what? KT. K into dt, sorry. K into dt. Now we will write this as dr by R is equal to minus K into dt. You should note, now integral of dx by x is natural log of x. Dx by x is natural log. When we say natural log, it is log to the base e. Log to the base e, not log to the base 10. So natural log is represented as ln. log stands for log to the base 10. So minus dx by x is what? Natural log to the natural log of x. Likewise, dt by t will be natural log of t. And likewise, dr by r will be what? Natural log of r. Did you follow this? Did you follow what I'm telling?
Yes, sir.
Natural log. Integral of dx by x is natural log of x. Integral of dt by t is natural log of t. Integral of dr by r is natural log of t. 1 minute. All right. All right. Now integrating both the sides. When we integrate both the sides, I have a confusion here. I don't know whether it's minus. We will see this minus and this minus. I don't know. We'll see. Integrating both the sides. Integrating both the sides. Integral of change in concentration of the reactant by the concentration of the reactant will be equal to integral of minus K into dt. Now we will write integral of dr by r is what? Natural log of r. What will be this? We'll keep minus k as constant, integrate dt, plus we will take dt constant and integrate minus k. So what is this? Natural log of r is equal to minus k into t. Integral of dt is what? T, we have been learning. Plus integral of any constant is what? 0. So I'm not writing 0. Whenever we integrate, we give an integration constant, and that integration constant is given as I. That integration constant is given as I. Let's see what's that. Okay. Integration constant is given as I. Let's see what's the value we get. And then now the next part of the topic is in the derivation. So far, did you follow? So far, did you follow?
Yes, sir.
Yes, sir.
Now the next is to find the value of R. Not value of R, to find the value of I. Now to find the value of I, we can write at time t is equal to t half. Not t half, what's that? T is equal to 0. At time t is equal to 0, at time t is equal to 0, what will be R naught? R will be what? We learned initial constant, half-life period. No, what's that? Time t is equal to 0. What's that? Time t is equal to 0. What is 0? R naught will be 0. Time t is equal to 0. R is equal to R naught. Sorry, R is equal to R naught. R is equal. I was correct only. Time t is equal to R is equal to R naught. So substitute this in equation 1. Substitute in equation 1, what do we get? A natural log of, this becomes what? R naught. R becomes R naught. That is equal to minus k to time becomes what? 0 plus I. So I will be equal to what now? Natural log of R naught. This you substitute in equation 1. Because we found out the value of I. What's the value of I we found out? Natural log of R naught. The value of I is natural log of R naught. That we are substituting in equation 1. When you substitute in equation 1, what do we get? We get natural log of R is equal to minus k into t plus of natural log of R naught. Now, if you take to the left-hand side, what do we get? This natural log, maybe we'll take kt to the right-hand side and ln of R to the right-hand side. So we can write kt will be equal to natural log of R naught minus natural log of R. Correct? Yes or no? It's rearranging the terms.
Yes, sir.
What is log A minus log B?
Sir, log of A by B, sir.
So I can write natural log of R naught by R. Is it okay? Log A minus log B can be written as what? Natural log of R naught by R. Now,
Yes.
Okay, now the space. All right, we'll see. All right, now we can write this equation. Can I write k is equal to, can I bring t to the denominator? Right side denominator 1 by t, natural log of R naught by R. Can I write? Can we write? I've just brought this t to the right hand side. When I bring t
Yes.
to the right hand side, it becomes what? 1 by t. Yes or no?
Yes, sir.
So how do you convert natural log to the base 10? So k is equal to 2.303 by t log to the base 10 of R naught by R. This is the rate equation for a first order reaction. See here, this natural log, it is log to the base e. Now if you have to convert it to the log to the base 10, the conversion factor is 2.303. When you multiply this value by 2.303, then this natural log gets converted to what? Log to the base 10. Did you follow? Did you follow this?
Yes, sir.
Now just take time to observe this derivation. For 1 or 2 minutes, you can observe this derivation. Then we're going for another derivation. It's a lengthy derivation. You follow it. It's an important question. And R naught is called as initial concentration. R is called as concentration after a certain amount of time t. Now, the same formula, we can also represent it as K is equal to 2.303 by T log to the base 10 of A by A minus X. This formula also you should remember to work out the problem. Both are same, but you have to derive in this fashion in NCERT. A is called as initial concentration. A is called as initial concentration. X is the amount of reactant reacted. So X is the amount of reactant reacted. So A minus X will be what? The amount of reactant left out after a certain amount of time. So let's go to the derivation quickly. Or 2 minutes, we can go to the derivation. Then we'll continue with one more derivation. Students, are you following what I'm telling? Or you just go through?
Yes, sir.
Mhm. Is there any clarification?
No, sir, no doubt.
Do you understand the derivation, students? Quickly.
Yes, sir. Understood, sir.
Followed or not?
Followed, sir.
Yes, sir. Follow.
Yeah. Ajay, did you follow? Yeah. You're not there in the class?
Sir, your voice is breaking.
I don't know, man. My system is okay, man. For another 5 minutes, you bear today, man. Last derivation, and then we'll stop. I don't know. My internet is good only.
Yes, sir. Now we can hear you.
All right. Understood this derivation? Okay. Now, derive to calculate the half-life period of a first order reaction. Or they can ask you, show that the rate constant of the first order reaction is independent of initial concentration. Initial concentration. They can ask you, based on this, they can ask you problems, or they can ask you, derive to calculate the half-life period of a first order reaction, or they can ask you, show that the rate constant of the first order reaction is independent of initial concentration. It's a very simple derivation. We'll derive it here. We will derive it. Now, can I say, we know that K is equal to 2.303 by T log to the base 10 of R naught by R. This is the relationship between, this is the equation to calculate the rate constant of what order reaction? First order reaction. We derived it now. Yes or no?
Yes, sir.
Now I can write at time, maybe I'll write it like this. At time T is equal to 0. What happens to R? R becomes equal to how much? Can I say initial concentration by 2? Half of the reactant is reacted. How much is left out? Left out will be R naught by 2. Did you understand? At time T is not at time T is equal to, at time T is equal to half, T half. Time T is equal to T half. Half-life period we are talking about. a time t is equal to t half, R will be equal to R naught by 2 because 50% of the reactant would have reacted. This is log. There's 2. What happened? Yeah. Yes or no? This will mark it as equation 1. Now these things will substitute in equation 1. Are you following, Ajay and others following?
Yes, sir.
Yes,
So when
sir.
you substitute, what happens? You will get K is equal to 2.303 by T half into log to the base 10 of, you have R naught divided by what you get? R naught by 2. So what happens on simplification? I can write K is equal to 2.303 by T half log to the base 10 of, this 2 goes to numerator.
So log
2
to base 10.
2 into R naught by what? R naught. So this will get cancelled. R naught and R naught will get cancelled. What is log 2 value? Log 2 value is log 2. You should know how to find the log 2. Logbook, it is 0.3010. Log 2 is 0.3010. So on multiplying, what do we get? We get K is equal to 0.693 by T half. So 2.303 by into what? 0.3010 is what? 0.693. So now in this rate equation, see, half-life period is there, rate constant is there. Anywhere concentration term is mentioned? Anywhere concentration term is mentioned?
No, sir.
No. That means this equation, rate constant of first order reaction is independent of what? Initial concentration. That is what I told you here. Derive to calculate the half-life period of the first order reaction or show that rate constant of a first order reaction is independent of initial concentration. So the derivation clearly says that rate constant is independent of initial, or the half-life period is independent of initial concentration. Just go through the derivation quickly. Let's see, 4 derivations we have done. Go through these 4 derivations. We have to do one more derivation possibly in gaseous state. We will do it. Go through this. All right. Any clarification with this 4 derivations?
No, sir. Not it.
No doubt. Can you do it? The 4 derivations?
Yes, sir.
Yeah. Okay. So the next derivation is derive the first order reaction rate constant, but in the gaseous phase. This derivation we are supposed to do. K is equal to 2.303 by T log of Pi divided by 2 Pi minus Pt. So this is in gaseous state. Earlier derivation, what we've done was in solution state. Solution state means we use concentration. When you're talking about a gaseous reaction, we cannot use concentration. We have to use the pressure. So Pi stands for initial pressure and Pt stands for final pressure. So rate constant for a first order reaction in gaseous state is K is equal to 2.303 by T log of Pi by 2 Pi minus Pt. Now we will derive this equation in the next class. All right, and then we'll continue with some of the questions based on these concepts what we have learned. All right, madam, can I stop, ma'am?
Yes, sir. Thank you, sir.
Yeah, ma'am. Thank you, everybody. Bye.
Thank you, sir.
Bye.
Thank you, sir.
Yeah, bye.